Hello, everybody. We'll continue chapter 5, and this is 5.2, the definite integral. And so you need to, of course, watch 5.1 before this one. And this is something we discussed in 5.1. We have a limit as n approaches infinity for this summation from this lower limit I equal 1 to n, and this product here that's going to be sum f of xi star, which is a sample point, times delta x, which is the width. And the long form of it means this: you're going to sum these parts towards to get to try to get a true value, and that comes from computing an area. Okay, and we also saw that it rises when we worked on the distance traveled by an object, and so the two problems in 5.1 were the area and the distance. It turns out that this is the same type of limit occurs in a wide variety of situations, even if it's not necessarily a positive function. So here we'll define the integral by having a function defined on AB, a closed interval, and we divide the interval into n subintervals, the ones we call strips there, with the width of b minus a divided by n. And just like discussed in 5.1, you have the x0 is the a, and the subparts until you get to xn, which is the b, which or the end of the interval. So being the endpoints, and you have these sample points which are somewhere in the like a center or in between, depending on how you want to take these sample points, like the intersection of or interception of the graph with the top of these strips, just like the pictures in 5.1. Then the definite integral of f from a to b is this symbol here, which is by Leibniz and called the integral. And I think it came from based on this story here, that's it's a stretched S, right? Kind of S based on the sums. All right. So what does this mean? The integral from a to b for the function f of x d of x is that limit as n approaches infinity for this sum of these parts by having as many parts as possible, because we saw in 5.1 you get a true value when you do that, provided that the limit exists, of course, gives the same value for all possible choices. If it does not exist, we say that the f is integrable. If it does exist, of course, it's integrable. Like we say differentiable in previously, now integrable on AB. All right. So what else you need to know in this picture and this notation is the integrand, just like we say radicand, for example, we say, let's say here the inside is the radicand for, let's say, radicals. Here we say the f of x integrand, right? And a, b are called the limits. So this is the lower limit, and this is the upper limit. And d of x for now, although it says here it has no meaning, but it does show the independent variable that is used. So this serves the purpose. And we saw what it means in differential calculus part, right? So for now, what you need to know about it when it comes to integral, that it indicates the independent variable which here is x. So which is, we saw it's important for when we differentiate, we need to know what we differentiate to, because if it's constant with respect to that, it's 0. If it's not, then we differentiate like we did in the related rates problems. R sometimes is constant and R sometimes is changing, or same for the height. So it is important to know the independent variable here for the integration. So the definite integral in this section 5.2, it does not depend on x. In fact, we could use any letter in place of x without changing the value of the integral. So what does it mean here? Not, to confuse it with that part of differentiation. It just means here that you can come up with, just like maybe here to understand it this way, I can say I have a number plus 2 gives me a 7, and I can call it x, or I can call it t, right? So this is really what it means. It doesn't mean that it's irrelevant. It means that you can put t and still come up with the same formula that's needed for the integration. So same thing here. We can still come up with x as 5 or t as 5. So that's what it means. But of course, once you put x or t, that means here is the independent variable is t, and here the independent variable is r, and this, but depends on the function. If the f of x and f of t and f of r are the same, they are going to lead to the same integral. And this sum is called Riemann sum, based on this mathematician, and we're going to work on it and understand it. This way, when we transition to the fundamental theorem of calculus, we have a much better understanding and how everything got combined, just like these strips or slices, how they all form the area. So the Riemann sum, which is the part of the summation from 1 to infinity, and this product of these two parts. So based on definition 2, it says that the definite integral of an integrable function can be approximated to within any desired degree of accuracy by a Riemann sum. All right. So we know that if f happens to be positive, then the Riemann sum in this case represents the, of course, the area, and can be as a sum of areas approximating these rectangles. So you can make these rectangles, add their areas, and you're going to find the area under this curve. And if the function is positive, that's a good thing to know, then the Riemann sum is the sum of the areas of this rectangle, right? So because we're going to see another case. So we see that this definite integral can be interpreted as the area, because f of x here is, remember now when we say f of x is positive, means it's above the x-axis. And so what happens if the curve goes above and below the x-axis? So what happens? Let's see. Here is a graph that shows that case. So here, if you do this, this area is going to be positive. But once it comes here, it dips below the x-axis. So the area here is going to be negative. And when it comes here, so you see, you start hearing something that, you know, not heard before. We know the area is always positive, but here we're talking about, of course, the definite integral, and it's almost like it has a direction here because it's above the x-axis, so this area is positive, and when it comes down here, it's negative. Then when it goes above, it's positive. So how does this affect what we say and what we do? It's this way. It's now called the net area. And that's something that's usually skipped in understanding this part of calculus. Because if we say that the integral is the area, we know that the area is positive. So, you know, how that resolves, how it resolves functions, let's say, below the x-axis, you know. So that's something to think about. So if f of x is above the x-axis, then we're talking about the area because that's positive, right? But if we have this case, f of x above on some interval, and f of x is negative, which is below the x-axis on some interval, then you're talking about the net area. So that's a very important thing to understand, and a lot of people don't focus on it at the beginning, and the confusion just grows after that. So if you have a function that's up and down like this, then this integral is the area 1 minus the area 2, where the area 1 is the region that is above the x-axis, right? And area 2 is below the x-axis, right? And if we understand this part, that's it. That's an important part to understand and keep in mind. So if somebody asks you what is the definite integral, the answer is not, it's the area, right? So because you can see here, it could be the area, or which is under the curve, if f of x is positive, but it could be the net area if some parts are positive and some parts are negative. And of course, if it's just below the curve, then it's negative, right? It's still the area there, but that area is negative. All right, so although we have defined this, of course, so, you know, this is similar to what we're talking about for a few minutes now. So we can talk about this theorem as we move on. If it's continuous on this closed interval and it has finite numbers of jump discontinuities, then f is integrable on AB. That is, the definite integral exists. So we'll see these examples will help. So theorem 4 we're going to apply, and this theorem 4 is going to be helpful, especially for those who are going to move up to other calc levels and deal with some other parts, and to train them for like the, you know, like the series and properties and stuff like this. But if those who are going to take just calc 1 and move on, probably after they do the fundamental theorem of calculus, they're going to stick to that part instead of coming back to this one. Some properties that we will use are useful for the integrals to know, because when you try to remember definite integral, first is you have these AB, right? That's in the definition. So let's make sure we stress on that. What makes it definite is that you have the AB, right? Because you could have integral just without the AB, and that will lead to a general form. But right now we're talking about these definite, but just what makes it definite is that closed interval AB. So here you have some properties that we'll be using, and they are useful. So the first one, if it's just that constant, and if you have a sum, then you can spread it as a sum. If you have a multiple, then you can use the multiple outside. If you have a difference, you see these are parts. If you have A to C and C to B, for example, then you can transition from A to B, of course, given that this is integrable there. This is, if it's positive, then that integral is positive, right? If f of x is greater than g of x, and so these properties are useful, and you'll get to work with them and understand them. And for 7, if f of x is greater than g of x, then of course on the interval, you know, to compare you have to have same limits, upper and lower. Then the bigger function has the bigger area, something like this, right? Or bigger integral. This one, 80, is just is more of property. 80 is more for estimation, not much to use really, because if you don't want to do the calculation and you want to just figure out, have an estimation, look at this property here. So if you have a number, then it's C times B minus A, right, for this integral, right? So here it's just you estimate, you say the lower, we can take a lower number, or like a minimum, right, and a max, like a maximum. Like you can look at it between the minimum and the maximum. And the value of the minimum one, you see this area under this minimum is this, so it's lower than the overall area under the curve. And if you do the maximum, of course, that's going to be something like, you know, like this whole thing. So the integral is going to be in between. So if you have the upper one, because it's quick to calculate, and the lower one is quick to calculate, and you say the area is in between. That's all it is doing. There is something we're going to use, is the midpoint rule. And as you see from 5.1 is that sample point, xi, you can take in the middle, and that may help to get a better calculation. And if you do that, then xi, of course, is the middle. So the x after and before, you add the 2, right, for the interval. Let's say this is, if this is xi, then this is xi minus 1. And this is the xi star, right? And the xi star, it's the middle, right? So it's going to be half of that. That's the midpoint. So if they are adjacent, like we talked about, that you can use this. So let's do an example from the homework. and let's use of course from the homework, and I think maybe this is number 5. Let's see if we make let's say you're given that you know that an area or an integral is 14, and this integral is 9, and this integral is unknown. All right. So this is the same function f of x. So we can we can set up. So we can set up 0 to 3 f of x d of x, and the next one is just going to start with that, which means the adjacent, right? And that's going to lead to an integral that's going to start from this lower to this upper. And 0 to 5 f of x dx, right? And right, so that's how the property works. And we know this is 9, and this is a known, and this is 14, and that gives us this integral to be a 5. Okay, so just re-explain there some of these properties, and we talked about the midpoint and stuff. So let's talk about one that's going to be a little bit longer example. And I put some stuff here, and that's the example that I mentioned, that if you're going up to next courses, subsequent courses, then the techniques in this example will reinforce your mechanical skills when it comes to the series and stuff. And also it will help everybody, of course, understand the next part of the fundamental theorem. But let's break it down. So here the example says, use the form of this definition of the integral given the theorem to evaluate the integral, this integral here, -2 to 0. So it's a definite integral, and the theorem talk about is the one here with AB, and it turns to a limit, and this Riemann sum there with delta x being b minus a over n and xi being this part. So we've done this in 5.1. It's just now we're going to stretch it. So delta x is 0 minus -2. So ab over n. So it's 2 over n. And xi, just like we did in 5.1. So maybe review, of course, 5.1 notes, and maybe see a video if. So that's going to be plus I delta x, which is -2 plus 2i over n. And that's what we did in that to find these limits. Now we set up the integral, which is -2 to 0, 4x squared plus 4x dx, which is equal to this limit with the summation I from 1 to n f of xi delta x equals to the limit of I equal 1 f of you see delta xi is what we found here as -2 plus I, which is from here, times delta x, which is maybe do a different color, which is this one. So that's the setup. Now what is f of x? This is f of x. Right. So we can go ahead and substitute. So use f of x as 4x squared plus 4x, and that gives us the 4 and x squared. We can take the 4 outside because we have a 4, right? So this is can be factored. So let's show it here. F of x is 4 times x squared plus x, right? So with the one property of the summations, you can take the 4 outside that we did in 5.1. So let's take the 4 outside. And you have a summation here, or a sum, and of -2 plus 2i over n squared for the x squared, and we're going to substitute this again into x times 2 over n. We also saw property in 5.1 that this part, since it's a number, it can come to the front here, right? So you have a 4. So maybe we need to show this part here. Let's leave it here. The 4 will come outside, and since a 4 is a number and it's going to come here, and you know with the limit it's going to transition here. So that's what will happen with the 4, right? We can remove now this one here. So this is, as I mentioned, it's going to be a little bit long problem, but it's okay because we need to understand what's happening with it. So after this, we need to break down this parts, right? We need to multiply. And this one is just what it is. There is no multiplication. So we reached now so far the 4 transition to outside of the limit. And 2 over n is a multiple, and that has n to it. And you'll see in a minute. So foiling that part, you should get. So maybe you want to pause the video until you foil it and see if you get this part, right? That's the foil part. Then the other part remove in parentheses is going to be this part. Then let's just simplify. And I need the limit before that. Into infinity. and we have a 2 over n. So it's for I squared over n squared minus 6i over n plus 2. And this is going to be broken into 3 parts. So you have from one property that we did, of course 2 over n is a common factor for them, but this is going to be broken into three of them. So you have this, and you have this, and you have this, right? So you have, so from one of the properties for the series from 5.1, you're going to get something like this, right? You're going to split it. And of course 2 over n is outside, and the limit as n approaches infinity is that, and the 4 is sitting outside there. All right, so we can apply more properties to this. 2 over n. Let's do this and show. So this is, again, I is from 1 to n, so this can transition here as a property, I squared, and the same for the 6 over n as a property. And this one is just that for now. All right, so now from 5.1, we have formulas for these. We have a formula for the sum with the c, we have a formula for the I, and we have the formula for the I squared. Maybe I'll drop them here as well in these slides. Let's do that. And these are, of course, from the pre-calculus review, and they're in 5.1, right? So you have them in review, pre-calculus, or see 5.1 notes. So if you have this summation, it can be changed to this, and these are their equivalent forms, right? If you have these types, and we saw also for the other ones. So what does this mean? The I square will be changed, and this one, remember, you have n times for this one here, so that one is probably the easier one, and we can do that. And we have a 2 over n outside, right? So this 2 over n as well is gonna go inside. So maybe you want to do that before you switch. So maybe I'll do it here, then we transition to another page. So the 4 is still sitting there. The limit as n approaches infinity, and you have 8 over n cubed. And of I squared minus 12 over n squared, I equal 1 to n of I, plus 2 over n, I equal 1 and 2. All right, and now you know that we're going to replace these with their equivalent forms in formulas. So based on this, right, and based on the other property as well that we know for the other one, we can go ahead and break it down. So you'll have 4 limit So 8 over n cubed, n times n plus 1, 2n plus 1 over 6 minus 12, n times n plus 1 over n squared. Maybe I should split it so when you look at it. 2, that's from that formula, plus 2 over n times n times 2, right? Because that 2 is n times, so 4 the limit of n approaches infinity, 4/3 n plus 1 times 2n plus 1 over n squared minus 6 times n plus 1 over n plus 4. Just to simplify, we'll keep working on it, simplifying. So one over n, because n over n is 1 over n, all right, plus 4. So this change to that. So this as well can become same thing. 2n over n is going to be 2. So this as well will become a 2 over 1 over n. And as well, this one, n over n is 1 plus 1 over n. We're trying to get what's common. If you have a common factor, you can change it to make it easier to do. So what happened right now is to explain a little more, because so it's not lost in all these steps, is we had a start with the summation, right, as based on the definition of these definite integral. Then we have the, let's go here, you see this is the definition. So we needed delta x and we needed xi. We found them, then we replaced them into this. And we have f of x as this function. So once we replace, then we go into substitution. And once we have the substitution, because the 4 is just a multiple, it can go outside this the sum here. And for the limit as well, remember this limit rules allows it to exit out. And this 2 over n, it has an n, so it can just come outside this sum here and stay there, because it has a connection with the sum. So we did that. We put the 2 over n outside, and we kept this. Then we tried to simplify until we got to these sums. Once we have these sums, we transitioned from the sum to non-sum formulas using some of what we know. So here we moved, maybe you can call it, to non kind of summation form, if that's you know, that's to show what the transition and what happened. So we moved to this non-sum form, And we try just to make it as simple as possible. Maybe you can factor something and whatever the calculation that you need, but also for the limit, because we know with the limit, as it approaches infinity, we've done it. If you have that theorem 1 over n, we did it with x. So for example, maybe we can add a note here. We did the limit as x approaches infinity for 1 over x is going to be 0. So we simplified these as well for that purpose. So we look at, so let's show here as well, n plus 1 over n, it's n over n plus 1 over n, which is 1 plus 1 over n. So we did this, so we have these nice places here, and we can now apply the limit. We can now evaluate here the limit. So as n approaches infinity, so we're going to have, let's say for 4/3, let's write it down, 2 plus 1 over n minus 6, 1 plus 1 over n plus 4. So 0, 0, 0, 0, right? So that's going to allow, and we have a 4 outside, and that's going to be a 4/3 times 1 times 2 minus a 6 times 1 plus a 4, and that's going to be 1/3. So the integral and you're going to see how the fundamental theorem of calculus will make this a super easy problem, right? But the main takeaway from this problem is, of course, you understand how these formulas work and how this addition of these parts and the partition works and all that, but also working with the series, because in other math courses, the series are going to be a big deal. So this will allow you to practice that. And give you here a kind of a visual to it, a visual representation to this example, which is you see, so this is a net area, right? Because it does switch from above to below the x-axis, so that 1/3 is a net area.